Hello and welcome to Aeolian environments. So the term Aeolian refers to deserts and wind. So most of what happens in the desert is related to wind when it comes to what we think of sand dunes. So it's an all-inclusive term, but so we're going to apply it to the desert realm. And I want you to take a look at this awesome place right outside of Bryce Canyon National Park. It's called Tropic Ditch. And I want you to just take a moment to kind of observe what's going on here. You've had a full semester of learning about clues in geology. It's a theme, right? And the clues that you see here, there's just so much going on. You probably see that waterfall, right? Super cool waterfall. But the interesting thing is this ditch is man-made. Now it's turned into a naturally flowing system today, a fluvial system, but it was built to provide water to the township of Tropic many, many decades ago. This area is arid. It's considered a desert. And when you look at it, you may see some really interesting rock formations, which you'll learn about. There's some spires. There are some hoodoos. There's a variety of different things that you can see here. You see chemical weathering, biological weathering, physical weathering, everything that you can think of, sedimentary rocks, just a lot going on. I'd even tell you in the area there's some igneous rocks. So by now in this semester, I need you to start linking all of what you learned and seeing holistically what's going out on when you see nature. That's the end game of this semester, this course. And hopefully when you are completely done and you're kind of on your own after this semester, you will start to see the physical world with a different perspective. And that's been my goal all semester. I absolutely love desert environments, Aeolian environments. In fact, I may very well retire somewhere out near Zion National Park, Ruidoso. I might even consider somewhere else in Utah or Arizona. And the reason is I love the landscapes. The geology is just phenomenal. But it came from somewhere, and that's kind of where I want to start today. This is a view right outside of Zion National Park in Utah. And landscapes like this don't just happen. Okay, there has to be a source of material that deposited these rocks. All sedimentary rocks work that way, right? Even if they're made in the ocean, there has to be a source of material that makes them. But in the case of what you're seeing in Zion, this was an Aeolian environment that created this back in the early Jurassic period, somewhere around 180 million years ago. These were the rocks that were made. But the source of the material came from the ancestral Rocky Mountains being weathered and eroded and deposited thousands and thousands of feet of sediment. Those got buried, lithified, remember that term, hardening of rocks? And millions of years later, actually tens of millions of years later, the Colorado Plateau uplifted. And when it did, somewhere around 15-ish million years ago, give or take a few million years, this area was uplifted, somewhat tilted, fractured, and erosion and weathering processes took over and began to make these phenomenal rock formations that we call desert formations. So let's talk about what makes a desert qualify as one. Deserts receive annual precipitation, and not all deserts receive the same amount. Matter of fact, there's some that are much drier than receiving 25 centimeters a year. But if an area receives that much or less, it qualifies as a desert. So there are a variety of deserts that are in super cold regions. Not all are hot. When you think about deserts, though, the amount of precipitation matters because it's going to dictate the ecosystems and the biology, the life forms that can live there. That's how the two disciplines of something like physical geology and ecology and environmental science kind of connect. So another characteristic about deserts, they are extremely dry in terms of air moisture. So if you spend any time in the desert, your skin would lose its natural moisture pretty quick. You'd see that in a few places, in your hands, on your face, even in your nose. That may make you laugh, but everything changes when you spend about 5 or 6 days in the desert and you haven't been there because it's so low humidity. And that low humidity is important to how the desert functions. The ecosystems, the plants, and so forth, they're all adapted to this low humidity and low precipitation situation. Another thing I'd like you to think about is the precipitation may or may not be in the form of rain. It may be a combination of rain and snow, just rain. But when deserts do get their precipitation, some interesting things happen. There's a distinctive place that we can find deserts, and most, not all, but most deserts are found right around the 30-degree north and south latitudes. In fact, 30% of the Earth's surface is currently covered with deserts. During the time of Pangaea, that likely was a much higher percentage within the interior of Pangaea that had, for example, what you'll learn about rain shadow deserts in a minute. But you can see that there's an exception on this map, which is the Sahara. And the Sahara is kind of an anomaly. There's a handful of other places that don't exist around that 30 degrees north and south latitude. But the Sahara is the largest desert that we have in the world, and it's also growing, I might add, and that's important to think about when we are considering civilizations, humans, and where they live. I want you to look at one continent that's dominated by aeolian environments, and that's Australia. So I've been there, and the outback is definitely a qualifier for an aeolian environment. Then there's some very unique environments along the coastlines that provide a completely different set of biomes. So in the desert, lots of stuff can live there. You just may not see it during the day. And when you think about deserts, sometimes people have this misconception that it's just desolate, there's nothing there, there's no life. It's just not the case. The deserts are thriving with life, and most of the time you need to be up at night to see it because most of the animals and so forth come out at night because of cooler temperatures, especially in your really hot deserts. You can see some during the day, and you need to think about the plants and the cactus or whatever might live there. They provide habitat that's super important for animals to survive. There are two types of deserts. One is hot and one is cold. And of course, temperature plays a role in the qualifiers for being in either category, but the very most important element of what determines the type of desert is the majority of how that system gets its precipitation. So a hot desert, for example, the Mojave, the Chihuahuan Desert, the Sonoran Desert in the United States, all of these deserts are hot deserts. Places like the Sahara are for sure hot deserts. Australia's outback is a hot desert. When you're thinking cold deserts, these are places that are in higher elevation and typically receive a majority of their precipitation in the form of snow. But you have to think about the definition of a desert. So it's receiving 25 centimeters or less of precipitation. So that means it's going to be arid, there's going to be low humidity in the air. And when you see a hot desert on the left and a cold desert on the right. This is the Gobi on the right, and on the left you see the Mojave. And you can begin to go, okay, I can see the difference. And you could imagine the weathering processes would be different based on how and what type of precipitation and how much an area receives. Some desert characteristics that are really important is that most deserts have lost a majority of their soil. So what soil does exist is usually very thin, not very fertile, and the plants that live there have to be adapted to a way to conserve whatever water it can receive. That's one reason you see a lot of cactus in many desert areas, but not all. For example, this is the outback in Australia, and you don't see a bunch of cactus there. There may be small ones, and there were when I visited, but what you see this, you see sagebrush and lots of gravel and very not fertile land. So you have to change the land use if you're going to use deserts for growing crops, and that does happen. Let's talk about an important concept relating to deserts as we get started, and that's the rain shadow desert. So we have a very famous rain shadow desert in the United States, which is Death Valley National Park. And that is in California, neighboring right on the west side of Nevada. So it is in California, so it's just kind of on the eastern side of it. So what has happened is you get one side of a mountain and it is very wet because the clouds are coming off, like in this case, off of the Pacific Ocean. And you get lots of moisture, and as those clouds go up the mountain, as you see in this diagram, they reach their dew point, and it condenses the water and precipitation comes out. Very rarely will these systems cross over the mountain, which means the air is much drier on the desert side. And that's what a rain shadow desert means. It means you get rain on one side and it doesn't make it to the other very often. So you get a mountain that literally does not, it like has two personalities. One's very lush and wet, the other is arid or semi-arid. Certainly the case for Death Valley National Park. When you think about that area, that's called an orographic effect, where a mountain provides a barrier and causes this phenomena to occur. So rain shadow deserts exist all over the world. And one thing I would point back to is Pangaea, me mentioning that there would probably be a higher percentage of deserts that existed back in Pangaea time frame within the middle of Pangaea or the interior of it. And a lot of it would have been because we had super, super tall mountains because continents had smashed together. So you'd have Himalaya-like mountains. And I would suspect that there would have been very minimal way for those rain systems to make it over the mountain. Having said that, in Death Valley and other rain shadow deserts, occasionally one of these storms does make it over the mountain. And when that happens, we have a significant downpour of rain. That can cause and does cause flash flooding. So in the desert, that is one of our big concerns. Let's take a look at Death Valley right now. And you're going, oh, wow, that's nice. But if you've been there, it's like, oh, wow, that's nice. It really is a cool place. And Death Valley is just one of the epitomes of the examples I can show you of what a rain shadow desert is. So parts of Death Valley actually exist below sea level, and when you get there, it is so hot. The last time I visited Death Valley, I was going to the Badland Basin, and this is actually the area that's below sea level. And what I was just floored by, the temperature that day was between 125 and it got up to 128 degrees Fahrenheit. And in the part of the day that we were in Badwater area, we came across this guy training for a triathlon. Go figure, right? But it's a thing out there in Death Valley. It's like the extreme of all extreme triathlons is for people to do this event in this harsh environment of the desert. So they do the swim on one side of the mountain or in a different place, and then they actually do the marathon in this section and bicycling in this section. Extremely dangerous. And he had a group of people following him with all the necessary, equipment and fluids to keep him safe. And by the time I got to the park headquarters, at the end of this presentation, I'll show you what the temperature was there at the park headquarters. It was so incredibly hot that I was trying to take some video with this very computer I'm recording with now to show y'all some of the sand dunes and rock formations in Death Valley, and it melted part of the exterior of my computer within 40 seconds of being outside. Not all deserts are that hot, but they can be, which is something to think about with climate change. As surface temperatures on the earth begin to rise, we would see an increase in areas that have lack of moisture, lack of humidity, much like deserts, and you could see the land change, which is part of the message about deserts. I know I told you that Aeolian means wind in deserts, and it does. And some features in the desert are primarily formed by wind. But when it comes to erosion, it's flash flooding, it's flowing water that does that. So I have not adjusted this picture or done anything to the color. This is in the Petrified Forest in Arizona, another national park. And you can clearly see there is this massive storm in the background, one that had been following us on field course that entire day, and we kind of stayed about an hour and a half ahead of it. And then it gained strength, and it joined up with us in the Petrified Forest, enough for the tornado sirens to go off. And I had students that were a good half mile or more away from the vehicle on one of these trails looking at petrified wood, and we could literally start to see horizontal rain, and the wind was just blowing all the quartz that had weathered out of these petrified logs straight into our faces. And I'm screaming to get back to the car because we know flash flooding is imminent. The last student gets in and we just literally pile in and go. And we are about a mile or two from where this is shown, and it caught up with us. We made it through the low water crossing, the very last one, as the flooding occurred, and we stopped on the other side and literally saw the washout of this happen in front of our eyes. After that event, I never saw the desert the same way. I realized it can change in a moment's notice. So we continued driving and made it to Holbrook, which is a good 45 minutes or so away from the park, because that's where we were going to stay. That's the closest thing to, in terms of lodging in town or city near the Petrified Forest. So much water dropped in an hour that it put about 3 feet of water in Holbrook. You're going, that's impossible. Well, there's a reason for that, because it's all desert and it's covered with something called desert pavement. So there's not much way for water to infiltrate and certainly percolate into groundwater. Instead, it just runs off. And when the dry washes fill up, they spill over just like a creek bed would, because that's exactly what they are. Dry washes are a form of creeks. They just don't flow all the time. When you think of the power of water, this is kind of what I want to show you. Both shots are of Zion National Park. On the left is a very sunny day. The irony was the day before a massive flash flood had come through Zion. But I want to point out that you can see where I'm putting my mouse, where water has clearly weathered and eroded that rock formation. That's the Navajo sandstone, and that is the name of the geologic formation. It's highly cross-bedded, and it is early Jurassic in age. And so that Navajo is important because we're going to learn about that today and show you just a lot of formations that are from there. On the right side is the same part. And you can clearly see it's raining. And do you see the beautiful waterfalls? Well, those just immediately started. So if you were hiking and came in contact with that, this could literally be a life or death situation. In the geologic perspective, we care about it because this running water is going to pick up sediments that can abrade and erode and literally carry out all these sediments that they weather and create canyons, which is exactly how canyons in the deserts form. This is actually in Bryce Canyon National Park, and can you see how a low water crossing was flooded out? And this is after the water went down. You can see the mud, and if you were to try to cross one of these things, it could be your last crossing. So I would encourage you not to, because the power of water could easily compromise a low water crossing because you don't know how sturdy the substrate is underneath these low water crossings. They could easily be compromised and weathered out, and when you get on there, that weight could be the angle of repose. It exceeds that, and you know what happens from mass wasting, right? It would collapse. So you need to be careful about approaching these situations. And I wanted you to see this because, again, people have a misconception that deserts are all formed strictly by wind. The formations and the radical changes that happen within the geology, meaning erosion, happens from moving and flowing water. Wind does play a role in shaping and abrading rocks, but it can't do the same work that flowing water does. This is actually in Saguaro National Park in Arizona, and I want you to take a look at this. This is a dry wash, meaning it would be, you could walk in and it'd be dry on most days. But during monsoon season, take a look at the devastation and how this could totally change the landscape. Not only would it weather and break up sediments, it would erode and create new cut banks and flood out sections. It's very dangerous. So when we have flash flooding in the desert, it's not something to dismiss. It's dangerous. And that's just part of living in the desert. So people just sometimes think no events like this can happen, but typically during monsoon season, which is late June to early August, this is a thing. And when it does happen, you need to be prepared for it. In the desert, we have numerous types of weathering processes. So you learned about mechanical, biological, and chemical, all of which are shown here. Usually you don't just see one type of weathering process in an area of a desert. You see all of them. Let me show you what's happening in these pictures. In the left picture is Bryce Canyon. This was on field course a few years ago, and normally you'd be able to see a panoramic view of hoodoos everywhere, which you'll see a little later. Instead, we got caught in a blizzard. I mean, we were setting up lunch the day this happened, and goodness, the biggest snowflakes I've ever seen started coming down, and it was a blizzard. Well, this area is about 9,000 feet in elevation, and so it does freeze most days of the year, like 3/4 of the days of the year. But this was an unusual event, especially for May. So the next day we go out so the students can at least experience and see hoodoos, and this is what we see. It was incredible. And hoodoos form because snow and the water as it melts gets into the joints and fractures of rocks, and then it expands when it's frozen and produces frost wedging, which is a physical type or mechanical type of weathering. If you see the tree in Zion in the middle, you can see how that tree could create biological and mechanical types of weathering. On the right, you see a form of chemical weathering called desert varnish. So even the color of the rock is oxidized, and that is happening in most all deserts. You'll see a combination of these things occurring regularly. So keep an eye out because it's pretty cool when you see them. Another weathering process is abrasion. So this is where the wind comes in. I took this shot along Highway 89, so this is going from Flagstaff in Arizona right along the Vermilion Cliffs, and we're past the turnoff to the south rim of the Grand Canyon. And this massive storm comes through. And it just all of a sudden popped up. So a little further down the road, we hit rain, but this was the dust storm part of it. And you could easily see how this wind picking up the sand, with sand out there having predominantly a hardness of 7 because it's made out of quartz, and that's what weathers out of the sandstone. This sand picks up and it can abrade anything, including the paint on your car. And it was a really tough storm. We had to pull over and kind of watch it because it was intense. And you need to be prepared for that if you live in the desert or visit the desert, that this kind of thing can happen. So let's talk about how wind does its work in the desert. It does create erosion. It's just not the most powerful force. Flowing water is. It creates weathering and erosion by moving sediments that are able to be picked up by wind, or at least pushed by wind. So let's talk about bed load. If you look at the diagram down here, bed load's going to be all the stuff that's too big to be picked up. So what happens is they're too heavy so to be picked up and carried in the air, so they're actually moved along, they're pushed along. And one rock smashes into another and helps dislodge them. That smashing we'll learn about in just a second. Some of those sediments are light enough to be picked up by wind, but here's the interesting fact. It is sediments usually that are heavy enough that you would see in that dust storm I just showed you. That would be things like sand that we can actually see, because there's a form of dissolved particulate matter that's in the air that's called dissolved load. And there'd be things like loess that you learned about in glaciers. It would also be maybe some silt that's in the air. But the suspended load is typically sand that we would see in the desert if there is something that size that can be picked up. So the difference between bed load and suspended load, bed load's what's on the ground. It can't be picked up typically by wind. The wind just doesn't have the strength to do that. And then the suspended load is what can be picked up and transported. So a really interesting phenomenon happens in the desert called saltation. And I like to think of saltation this way. I kind of circled where it's happening in the diagram, but I was mentioning that the bed load, one rock smashes into another and dislodges new rocks, or maybe breaks up a rock because one smashes into the other. So that's what saltation does, and it kind of moves things along at the bottom of the desert floor, because it's the middle side sediments that get to hop and jump and then bump into something else. So it's like bumper cars. That's what saltation is. Which brings me into how wind affects and shapes rocks. Whenever a rock in the desert is clearly affected by wind, it's been abraded and there's evidence of lots of wind weathering, then we call that a ventifact. Let me say that again, ventifact. Ventifacts are just a generic, all-inclusive term that talks about rocks that have been exposed to abrasion, typically sand from suspended load, and over time they get weathered into a unique shape. So you look at this rock formation and it has a cap rock, so technically it could qualify as something called a hoodoo. But wind is what really shaped this top rock and down here. And that's why it's called a ventifact. Let's talk about another important way that rocks are changed in the desert, and that's something called deflation. So I don't want you to confuse that with ablation from glaciers. Let me clarify the two terms, but they're kind of similar. Deflation basically means that the smaller sediments get taken away in the desert, and they are transported by wind. So you're looking at sands and silts and that dissolved, really fine-grained sediment. Over time, that means you get left behind with a lot of bigger rocks, which is why you develop what I showed you in the outback in Australia or here. And you can see that these rocks are much bigger, and then the ground is just very hard. If you walked on this, it would not be soft. It's called desert pavement. And so that's one reason they're dangerous when you have flash floods, because this area has a lot of rocks that kind of prevent that infiltration. Which brings me to desert pavement. This is actually in Death Valley National Park. And I want you to look at the amount of big rocks there that happen from deflation, and we're not going to be able to have a happy situation if flash flooding occurs out here. In fact, it would be, instead of a dry wash, it would be a roaring river when you have a flash flood. So if you get continued deflation over time, the top layers of the desert floor actually are taken away and you're left behind with all the heavy rocks. And this creates almost like a concrete surface that's made out of rocks, and that's called desert pavement. Again, that reduces the potential for infiltration and percolation into groundwater systems. When you look at desert pavement, this is out off of Highway 89 in Arizona, and you can clearly see that there's rocks everywhere. It kind of looks like there's a crust or a coating on the ground. Most of it, well, that is desert pavement. And this is important when it rains because there's nowhere for the water to go into the ground. It just washes off. Here's another example of desert pavement in Death Valley, and you can clearly see why you might have problems when you have a flash flood. So let's talk about how wind does deposit sediments. We've been talking about weathering and erosion. Let's talk about deposition. In some areas you can form sand dunes, but there has to be a source to create the sand. And I kind of started this conversation off by talking about the source of material for places like Zion and Bryce, that they had to be weathered from something to create the rock formations that were in the Colorado Plateau. So this is in Death Valley. This is where my computer melted. I had some video of trying to take these sand dunes right there. But I want to point out where the black arrow is. You can see there's a mountain in the background. So as that weathers and erodes, the eroded sediments can get picked up and turned into sand. And that's exactly what happens. So whenever you see sand dunes, it didn't just like fall from the sky. It had to come from the weathering of something. There has to be a source of rock that gets munched up like this and then drops into a common location. So that's one of the main takeaways of sand dunes, is understanding the source of material. So the bigger the mountain and the more erosive the forces in the desert, the larger your sand dunes are going to be. The smaller that is, the smaller the sand dunes typically are going to be. There are three things you need to make a sand dune. You need a steady supply of sand. You need a consistent type of wind conditions. That doesn't necessarily mean from the same direction. That's important to the specific type of dune. And there must be an obstacle that slows down the flow of the air. That could be a rock, that could be a mountain, that could be a car out in the desert, that could be a fence, it could be anything, right? A tree. And it just stops the flow or retards it and allows the sand to drop out. So thinking about that, there are a variety of different sand dunes, and we're going to learn about each one. And some of the key things you need to do is recognize their shape and recognize the criteria of what do they have: a lot of sand, not very much sand? Do they have constant wind directions from one way? Or are they variable wind conditions or from different directions? It'll make sense to you when we get through this. So one of the most obvious and easiest ones to recognize are Barchan dunes, which is what you see in this picture. And as you look at Barchan dunes, the obstacle where the sand's wrapping around, I'm just going to point to one right here. There's probably a rock here, and the sand is in the air, hits that, and wraps around it. So the wind direction actually, the tips of these things are pointing downwind because the wind is coming this direction. And that matters because when we get to a different type of dune called parabolic, it's the opposite direction. And the wind is very clearly coming at this area. So it's opposite. You'll see that. Anyway, these types of dunes have a constant wind direction. They have minimal sand comparative to most of the other types of dunes, and they have very limited vegetation cover. What are transverse dunes? These are very common dunes. They're long ridges of sand that are perpendicular to the prevailing wind. That means they're going to be intersecting this direction. These dunes have a constant wind direction, minimal vegetative cover, that should be a theme with all of these except for one, and an abundant amount of sand. Going back to the mountains, do you see a source of potential sand in the background where these mountains exist back here that could weather and erode and produce the sands necessary to make transverse sands? So linear or safe dunes, and they're one and the same. They're just different names wherever you might be in the world. I kind of like the name safe myself, but linear dunes are very easy to recognize because they have long parallel systems of sand that have been deposited one ripple after another. And they come and develop because you have a very consistent wind direction. You don't have nearly as much sand as you would for the last type, transverse, and you have very limited vegetation. This is White Sands National Monument in New Mexico, and the sand is just beautiful. Interesting tidbit about this particular desert. This is not made out of quartz-based sand. It's actually made out of gypsum because the mountains in this area, the Tularosa Basin, is very enriched with gypsum. So as those rocks weather and erode, the gypsum with a hardness of 2 ends up being the deposited material. So it's very soft. And if you go out there and ever get to the park, I want you to feel the sand and notice that because it's really one of the cool facts about this location. All right, I was talking about a dune that formed the opposite way from Barchans, and this is it, parabolic dunes. There's something unique about parabolic as compared to all the others you'll learn about. This one has vegetation. So you will typically see these along coastlines. And the vegetation plays a very important role because it kind of anchors in the outsides of it, and then the inside kind of makes a bowl-shaped feature where sand collects. So if you've ever walked a beach and you see an area where there was some vegetation and then there's just a thick amount of sand, you might be walking in a parabolic dune. These dunes have a constant wind source, and the wind source is coming from the ocean directly at that coastline. And so it blows out a hole here where the sand collects. And so it's facing the opposite direction. The open face of it's actually facing towards the wind, where Barchan, the open face of it, is on the back side of the dune. So they're very different. So again, parabolic dunes form typically along beach lines, and they have a hollow section, a center. They're very distinctive looking as compared to the others. There's still another type of dune called star dunes. These are probably the most majestic of all dunes, and you have multiple arms that develop in a dune in all different directions because you have variable wind conditions, and that creates variable slip faces where sand will come down and deposit on various sides of whatever obstacle it hits. These dunes are going to have an enormous source of sand. So you've got to have something that produces that sand, that weathers and erodes it. So there's got to be a mountain range somewhere that's doing that. Variable wind conditions and probably the least amount of vegetation of any of the various different types of sand dune situations. So sand dunes are not everywhere. Not all deserts have a concentration of sand dunes. And that has to do with the weathering conditions and the bedrock. So now that you know that dunes require the erosion of something to produce the sediments, you'll probably see them with a different perspective or lens when you go and you see sand dunes. All right, another important Aeolian landform is crossbedding. Now, you've learned a lot about crossbedding this semester. It's time to learn about Aeolian crossbedding, and there's no place in the world you can see better crossbedding than here. This is Zion National Park in Utah, my favorite national park. And what happens is sand grains get blown up onto in the desert, and then they topple down the other side. Another layer comes in, does the same thing. So you get a crisscross pattern over time, making this one of the most phenomenal of all Aeolian landforms. So the angle of the crossbed matters. As you learned in fluvial, low angle crossbeds are formed in rivers. They can never reach the same angle of repose that dry sands would. And so really high angle crossbeds immediately tell a geologist, it's a clue, it's like, clue, this was formed in a desert. And so sometimes we see areas that we suspect should be crossbedded and they're not, like Sedona, Arizona. And they were at one point, it's just something happened that kind of smoothed out those crossbeds. And that would be like a marine transgression. But certainly that did not happen here. So I'm going to show you crossbedding. And this crossbedding is just phenomenal. And you're looking at that and you're going, holy moly's. So this is not just one dune. This is a series of dunes that formed in the Navajo sandstone. So it's early Jurassic. And you can see the crisscross pattern. And sometimes you'll see a flat section where it looks like the crossbeds have just been wiped clean. I'll tell you what that is in just a second. For just a minute, I'm going to take you live to Zion National Park, and you can actually see and imagine that this area once was a massive desert like the Sahara. Look at the angle of the crossbeds, and you can almost visualize how they formed if they were still sand today. The color differentiation has to do with porosity and permeability that you learned about in groundwater. So the redder the rock, the tighter the porosity, water didn't flow as well through it. And the whiter that same rock is, the less or more permeable those rocks would be, like the ones you're seeing here. But it's all the same geologic formation of the Navajo sandstone, highly cross-bedded from the early Jurassic period. So a good shot of video showing you one of the most remarkable places to see crossbedding in the world. But nevertheless, this is crossbedding and something that is phenomenal. I've never seen crossbedding as awesome as what you see in Zion. So when you see high angle crossbeds, think right away it probably was an ancient desert. So Zion would have been like the Sahara today. So if the Sahara gets lithified, meaning hardened, we may have another Zion National Park in Africa somewhere in the future. I would love to see that and see how awesome it looks. So this is different shots of Zion National Park, and you can clearly see the crossbedding, the way that the sediments have been blown and laid on top of each other. And that's the phenomenal thing, that they were buried that way and didn't lose their shape. Here's another shot of crossbedding. This is also the Navajo sandstone, but not in Zion. This is in Antelope Canyon, to be precise, Lower Antelope Canyon near Page, Arizona. That's where Glen Canyon Dam was built. So I was talking about the Lake Powell. This is where that is. It's Page, Arizona. But there's a really beautiful set of slot canyons that people like to visit. One of the most photographed slot canyons in the world is the upper and lower Antelope Canyons, which is in this cross-bedded sandstone right here. So I told you I'd tell you when you see a crossbeds and you see a top that's been wiped off, and clearly that's happening here. Can you see the crossbeds, and then you get a flat line and then a new set of crossbeds? What's really happened is a storm came through and wiped it clean. And then new sands are put in top. So in theory, you could call that an unconformity, but these sands were deposited in sequence, meaning they're similar in age. So I don't know if I quite call that an unconformity, but it looks that way when you see it. But they are simply, this one in particular is really good. You can see the angle, and then it's wiped flat and new ones are put on top. That's called a truncated dune. So the newly eroded layer gets fresh stuff put on top, and it just starts over again, and then the next storm system wipes the next crossbeds. And so typically in heavily crossbedded units like the Navajo and Zion, you'll see this phenomena over and over and over in the same large rock formation. Here are some truncated dunes on the east side of Zion. There's two sides to Zion. The east side is my personal favorite just for the drive itself. It's just gorgeous because that's where all this heavily cross-bedded stuff is. But the east side is where you do most of the hiking. And it has a whole different phenomenal beauty to it. But the whole park's just awesome. And if you get a chance to go, this should be on your bucket list. But you can see this truncated dune here, one here. There's some more up in this way, but again, the truncated dune represents crossbeds. You get a storm, this crossbed is wiped flat, and the new ones are put on top. Another thing that we can do to determine what type of rock we have in dunes is to look at the sand grains themselves. So frosted sand grains indicate that they were made in dunes that were formed inland. And what do I mean by inland? Away from the beach. Okay, so they're like in interiors of continents. So we'll talk about Zion being in Utah. Just by its proximity today doesn't mean that it couldn't be at a beach line in geologic past. You should know by now that sea level rises and falls, so the coastline changes regularly throughout geologic time. So if we get a close-up look at sand grains, and they have a frosted appearance like these do, then we know that they were grains that were formed in the desert because they smashed like marbles, like clear marbles, and they have a kind of a look to them of frosted that marbles that haven't been smashed don't appear. So if you have beach sediments that are sand grains, they don't have a frosted appearance typically because they're lubricated by water, so those grains don't smash the same way. And that's one clue that geologists look for to determine if you're looking at sand grains that are from Aeolian or from beach environments. So I mentioned Sedona, Arizona. That was the secret to kind of unraveling how that area looked, because geologists were like baffled, why aren't there any crossbeds in the rock formation that makes up most of the area, the Bell Rock or Schnebly Hill. And what it took was a geologist looking at the sand grains to see that they were frosted. And so the hypothesis was that marine transgression came in and smoothed out all those crossbeds. And that's why we don't see the crossbeds, but we have the frosted sand grains from when it used to be much like Zion. So looking at this is an alluvial fan right here, but you need to understand that this is like a mountain and you're not even seeing all of it, but water is draining off of it. Let's call it a mesa. And water is draining down, and any sediments it carries gets deposited on the desert floor and kind of spreads out. When this happens, these alluvial fans provide deposits. And so especially ancient alluvial fans can be very beneficial because they can be highly fertile and also be used as construction material. So the same thing can happen along a mountain, and water drains and deposits alluvial fans at the bottom. In layman's terms, when we see this kind of thing in mountain ranges, we call it a talus slope. And one of the things I'd point out is alluvial fans and talus slopes typically have very angular sediments that didn't travel very far by water. They just kind of fell off of something. And that's certainly the case in mountainous alluvial fans. When you get a multiple alluvial fans that start to join up, this is in Death Valley, they start to spread out and their alluvial fans begin to connect and kind of become a family. We call that a bajadas. And a bajadas are actually kind of cool because in places out in the desert in the United States, especially where the citrus farms are, maybe down by Tucson, there's a lot of bajadas, and they provide the fertile soil that is enriching to help them grow crops. So the next issue would be, how do you get the water? That's a whole nother concern when you're out in the desert, if groundwater or surface water is available. And we've talked at lengths about that in this course. But I like bajadas because they're kind of neat where all of these alluvial fans kind of join together. So you see an alluvial fan coming this way, one from this mountain, one from here. So I'd kind of compare that to what we see when glaciers, valley glaciers, enter the same basic lower valley and you start to see medial moraines. It's kind of like what you're seeing here with desert alluvial fans. Playa lakes. So playa lakes, we actually have these in Texas, and you can see them out by Lubbock and Amarillo. And what will happen is either rain or groundwater will fill up a small flat area, depressed area, and you'll get water temporarily. This becomes an important water resource, especially for wildlife, and as it evaporates, it can leave behind evaporite deposits such as gypsum or salt, halite. And that is useful. So playa lakes are usually dry, and then let's say you get a heavy rain out by Amarillo, there'll be lots of these things that pop up, and then maybe a week or two later, they'll be gone. And playa lakes are, again, important water resources out in the desert. So what's a pediment? These are usually at the base of mountain ranges that have weathered down, and this is just kind of the remaining low relief structure. They are not a mountain anymore, but they definitely are bedrock. So occasionally you'll be driving and you'll see what looks like a miniature mountain. Those are typically called pediments. So on field course, I will usually have a student or two say, "What's that thing? It looks like a miniature mountain." Well, it is. It's a pediment in the desert. So if you see something that looks like this and it's just sticking up and it's not like tall enough, doesn't meet the requirements to be a mountain with a certain number of feet with a summit, then that's probably a pediment in the desert. A very important aspect of deserts are dry washes, and I've already talked about these, but I wanted to show you one because you'll see them all over the desert. You'll see lots of dry washes, and they even have names, like this is Echo Wash. But these desert creek beds that are dry become raging rivers when you get a flash flood. And you can clearly see the power of erosion if you kind of hike down a dry wash or even look at one from the road and see how powerful water can be in the desert. Another important landform is a mesa, and a mesa is going to be bounded on all sides by a steep topography and a relatively flat top. And that's exactly what the word means, is like tabletop, flat. These things are much wider than their cousins known as buttes. So mesas, this one here is in Canyonlands, and I want you to notice that it's relatively flat, and you can see more in the background right here. So when you get these steep slope features and a flat surface, and they're fairly wide, that's called a mesa. Buttes, however, are different. So I know online you can see a lot of definitions that buttes are just weathered down mesas. There's some truth to that, but they have a different appearance. They're not nearly as wide, they're skinnier, they're steep, and they usually have a bumpy or irregular top like this butte in Sedona. So it's not flat on top. This is another butte. This is actually Bell Rock, very famous place to hike, and Sedona, Arizona. It has a bumpy top. It qualifies as a butte. When you see the difference between buttes and mesas, on the left where the blue arrow is pointing, you can see the flat, broad-shaped features. Those are mesas. On the right, you see the bumpy. It's not nearly as wide. That's a butte. So knowing the difference between the two helps you delineate what you're seeing in the desert. My personal favorite landform in the desert is a hoodoo. And hoodoos form by a unique process of primarily frost wedging. But you have to have a couple of requirements. So do you see this thick surface at the top on all of these? That's called a cap rock. And the cap rock is a tougher rock than the rest of the hoodoo. So in Bryce, these rocks are Cenozoic in age, so they're younger, much younger than what we see in Zion. And these are softer materials. This is the harder material. So a hoodoo, by definition, you'll see the terms in books and in definition dictionaries as a tall, thin spire. I will define a spire in just a minute and show you the difference. A spire is a tall, thin thing, but doesn't have a cap rock. So you've got to have that cap rock in order for it to be a hoodoo. I want to point out how these structures look like they're almost a line of them. That's referred to as a fin, F-I-N. And the frost wedging, when it snows or rains, gets into these fractures and busts them apart and creates this phenomena here. So going back to one of the very first things you learned about were principles of geology. This is the law of lateral continuity. It's all the same geologic formation. Bryce is really high in elevation. It's around 9,000 feet in elevation. And so it's high enough that you get snow most of the time. So this is not a cold desert though, because it certainly gets hot there. But the point being is that the snow, as it falls and melts, it can get in these fractures and joints and do a really powerful form of physical and mechanical weathering known as frost wedging.
At Bryce Canyon National Park, we're here in a snowstorm. We arrived yesterday, but this is important to see for a couple of reasons. We had rain and snow, and of course it's below freezing. That adds to the weathering element of hoodoos. So a couple of things you need to form hoodoos is high elevation, wet enough conditions that you can get frost wedging. So you might go, well, there are a lot of areas in the world that could have that. That's true. So you got to have the right geology too, with the cap rock that's harder than the rock underneath it. But just as important, this area was uplifted back when the Colorado Plateau started uplifting, right after and during part of the Laramide orogeny, which is a mountain building event. So as you're seeing this, the area also got fractured and jointed, not just from the orogeny, but also from the stress put on by the Basin and Range province as it got stretched. So these fractures or joints are a key element of why hoodoos form in this elevation. While you can't see the massive amphitheaters, I'm only showing you what we can see visibility-wise today. Imagine that this goes on for several miles. It's really quite impressive. And that this has formed in late Cretaceous, early Cenozoic aged rocks, and it's continuing to weather back. So it makes these fins like this one right here, and the frost wedging helps break them apart where the joints are made from what I described earlier from the orogeny and the Basin and Range stress. And then they get busted apart and they make individual hoodoos, more like what you're seeing back here. So more to come from Bryce Canyon National Park.
So hoodoos form that way, and this is the highest concentration of hoodoos in the world. And I want you, if you ever get a chance and you're going to Zion, it's just about 2.5 hours away from Zion in Utah. This is totally worth the visit. It's beautiful. And the forest on the other side of it, where the first thing I showed you in this presentation at Tropic Ditch, it's beautiful. That's where the Dixie Forest is. You'll kind of go that direction and see it. It's really quite gorgeous. So here's the difference between a spire and a hoodoo. Can you see what happened to that poor hoodoo on the left? It lost its cap rock. That's a spire. So the one on the right, the twos that I have the red arrows pointing to, clearly have cap rocks on them, right? At some point, they may very well lose that cap rock and they'll become a spire. And ultimately, this spire right here, this is probably going to be weathered down in less than a year. It'll probably just disintegrate. I've been following hoodoos in Bryce now for a good 20 years. And in Tropic Ditch area, where there's just all this concentration of the Claron Formation, which makes these hoodoos. And I've seen spires disappear in less than a year. So it's kind of a unique thing. This is what it looks like at the top, because you are looking at what's the basin where all these hoodoos form. This plateau here is weathering down, and as it does, this is the rock formations that were in here. So you have to imagine that most of these rocks were formed in a lake environment, like the Great Lakes, and maybe some fluvial stuff as well. So this is not the same as the Navajo formation we looked at Zion. It's much younger and it's made a different way. And that's one of the contributing factors to how these hoodoos exist and why they weather the way they do, because the cap rock is a harder substance, allowing these things to form hoodoos. Another important Aeolian landform are arches. This is Delicate Arch in Arches National Park in Utah. You're hearing a lot about Utah, right? There's 5 amazing parks there. Different, each one of them very different. But arches formed by differential weathering, where you can get the same rock formation that weathers in different ways over time. Could be by chemical weathering, physical weathering, processes usually combined that will make that happen. In this case, the sandstone is being weathered, and the arches typically start off as the similar like hoodoos, and they are made in long fins, and then part of it disintegrates. This is not typically done by flowing water. It's done much like a hoodoo. But you could see how this thing could break, right? And that it might not stay an arch forever. Arches don't all look the same. Here's an arch called El Malapais, and it's in New Mexico. Beautiful. By the way, do you see the chemical weathering, all the deposits, and you can almost see where the groundwater oozed out of this thing and chemical weathering occurred, desert varnish. So arches are unique and they don't last forever. So when you're looking at them, the beauty of them is in the eye of the beholder, but this arch one day may not be here even in our lifetime. And so I would encourage you to look and see when you're looking at these rock formations, the potential for mass wasting to occur. One of the most magnificent of all of the desert landforms are slot canyons. This is a real place, and yes, it looks like this. This is Antelope Canyon in Page, Arizona. It's on Navajo Nation's land, so in order to take a tour of it, you have to go through them. What's the message here? This Navajo sandstone, the same stuff that's in Zion, this got made because of repetitive flash flooding. And you can almost see where the water picked up sand and abraded the sides of this insides of the slot canyon. And so what it does is cut right through rock, through this Navajo sandstone, and it literally makes an opening. When you see a slot canyon, that's a clue that this area is prone to flash flooding. In fact, some people died in Antelope Canyon, some tourists, a group of them, one year because of a flash flood that came through the area. Now it's really hard if there's been any rain upstream where it could flood. They don't do the tours because there's such a risk for people not being able to get out of the canyon because the water rises so fast. This is another slot canyon. This is the same geologic formation, but it's in Zion. This is the Narrows. And I want you to notice that you can see where the Virgin River is cut through this, making slot canyons. And folks, if you go to Zion, this place it rocks. But be prepared, it's cold water. You'll go brr, and you can hike up the Narrows. It is so worth it. even for all the cold, because the view is just spectacular. Let's talk about desert varnish, because it's everywhere out in the desert. This is a form of chemical weathering, and it will coat sandstone with manganese oxide. Manganese oxide, you need to remember that. And that's what causes the dark red and brown coatings that you'll see. Some like this doesn't seem that impressive, but when you see stuff like this in Zion, you're like, wow, it really makes remarkable changes to the rock. And again, it's a form of chemical weathering, so it can contribute to the formation of jointing, fractures, and certainly rock slides can be enhanced by lots of chemical weathering in conjunction with physical weathering, even biological weathering. Do you see the desert varnish right in here? And by the way, all of this is oxidized, but this is the varnish right in here, that really dark stuff. I should point out that desert varnish is also important for petroglyphs and archaeology. Native peoples figured out that they could easily draw pictures into desert varnish, and so oftentimes petroglyphs are associated with desert varnish. Another landform is called badlands, and badlands are just a generic term applied to barren landscapes in the desert like this. This is the Chinle Formation along Highway 89 in Arizona. Also the rock formation that is infamous for containing petrified wood in the petrified forest. But badlands aren't just allocated to one geographic location. There is a park called Badlands National Park in South Dakota. And it's very barren, looks like this, but typically it's a term applied to a region in a desert that is barren landscapes with very little or no vegetation. This is a form of badlands in Death Valley. So when you think of this region, I want you to be thinking, okay, this would be a pretty tough area to live. And it is, because it is very dry, very barren, and that's one thing to keep in mind as you're traveling through the desert. See if you can name the landform. This is where the rocks become bigger in the desert floor, preventing infiltration of water, also contributing to flash flooding. And if you guessed desert pavement, that was correct. Look at the desert formation. This is in Sedona. And what is it? It has a bumpy top. Is it a mesa or is it a butte? This is shaped by wind. What do we call the generic term for something that's been impacted by wind? Ventifact. This is that manganese oxide. What do we call that? This is a really good example of how and what this does. It's that special coating we just learned about. Desert varnish. This is that flash flooding that creates these remarkable scenic things. This is Antelope Canyon, so yes, it is a slot canyon. Is it flat or is it bumpy? That will tell you if it's a mesa or a butte. That's flat, so which one would it be? This is those water ponds that form out in the desert. This is out by Lubbock and Amarillo area in Texas after a rain event. So what do we call those? Those are not stock ponds, by the way. Playa lakes. What are those cute things? Well, I'll give you a hint. It's an Arches National Park. So yes, those are arches. They also have a special name when they kind of make this kind of feature. They're also called windows. But arches, you could see how the top of that could weather over time, differential weathering, and collapse. What is that? An alluvial fan. This is that barren landscape. This is out in the petrified forest. So what do we call that barren landscape with minimal vegetation? Badlands. This should be obvious to you what it is, the crisscross that we learned about. And indeed, that is crossbedding. These are prone to flash flooding. It's dry right now, but this dry wash could become a raging river with just an inch or so of rain in the desert. I hope you know what this is called. It's my favorite one. I even have a cat named after this. Has cap rock on top, If it didn't have a cap rock, it would be a spire. So what is this particular geologic formation? It begins with an H, so it's a hoodoo. That does not have the cap rock, so that would be a spire. So let's apply what you've learned and talk about desert issues, because there's lots of things to contend with in the desert, and one is mass wasting. So I've talked a lot about this in various presentations because I think it's important for you to connect the dots and link how the course content is related. This is Zion National Park right after basically a mudslide came through. It was flash flooding, and we were there 12 or 14 hours after it happened, and you can see this type of phenomena occur. So this is actually in Springdale, right at the western entrance that you would go in for most of the hiking in Zion. And this flooded out a section of Springdale and the campgrounds that people stay at right at the park. And this is the pool. This is this back side of the building. And on the front side, the mud line was much higher. It destroyed everything they had. It's kind of sad. When you see rocks like all of these, they came from up here. Those are rock falls and rock slides that can create this, and that can happen at any time. So people often find themselves in trouble because they don't pay attention to the warning signs that say rock falls, beware of rocks, watch for rocks. There's a reason for that. Some of these things end up in roads and on cars. So just be aware that these rocks are constantly mass wasting. Then you get mass wasting issues from flooding. This is what happened in Ruidoso, and you can see that the flood event there created what happened in this house and washed out a bridge downstream on this particular river. But these all happen in deserts. So even Ruidoso isn't part of a desert, it's just in a higher elevation. Then you get this type of mass wasting. Do you see where there was a rock slide here? This is a huge vista, meaning a giant rock formation. And the whole section slid off. And when it did, it was an instantaneous mass wasting. There have been several of these events in Zion that have trapped visitors in the park for several days because it blocked out roadways, and they'll get it cleaned up. And the interesting thing is when you drive through this, you can see all the giant rocks that fell off way down here. And so that's something to think about because these mass wasting events do happen. So why did it give way on one day? Enough chemical and physical weathering and the angle of repose was exceeded and mass wasting occurred. So rock slides are very common. Rock falls are common in desert environments. This is an example of one of those events. This goes with that. And so these big blocks of rocks you'll see along the sides of roads, that's a clue that these things fall off. People didn't move them. Nature let this fall off. Since this thing hasn't been rounded, we know it hasn't been picked up with water. It's just fallen in its place right off of whatever it came off of, which is that rock formation. This is some more flooding in Springdale, and the mass wasting, when it happens in the desert, it's typically alarming. If it's not a rock slide or a rock fall, it's typically due to the erosion of flash flooding. And I keep coming back to that because people think deserts are void of water. They may be low in precipitation and humidity, but when that precipitation happens, horrible consequences can occur, such as this. This was some of the appliances in that hotel or motel RV park that got ruined. And you can see these were things that were on the first floor. This is right near the entrance of Zion. And you see footage from this event, like video footage. It's kind of compelling. You're like, wow, it's amazing that more damage to humans didn't happen. You see something like this in the desert, you get very barren landscapes, and you get that frost wedging, and you get runoff and so forth. It compromises the substrate, making it very prone to mass wasting. This is biological weathering in Ruidoso, and can you see how it's totally eating away the rock and not allowing for vegetation? You see this kind of thing, you need to go, that's a problem. I need to be careful about that because I need to recognize that mass wasting could happen at any time. Another problem in the desert is air quality. And this can happen because of suspended material that gets into the air, like a dust storm. And this is a dust storm not too far from Phoenix. And we were out there and this came in and couldn't see a thing. So these things do cause problems and they present issues for the people that live there. Air quality conditions for dust storms can reach hazardous capacity, even by EPA standards, for making the air unsafe to breathe. The most probably important topic to talk about with deserts is climate change. And by now you've heard a lot of climate change information. So I'll link back to what you learned about in glaciers and say that albedo of the earth is that reflectivity. The warmer the surface temperatures get on the earth itself on land, the lower the albedo gets, which means we absorb more heat. And as more heat is absorbed, places like Death Valley or any of these deserts, it becomes exaggerated. And we can get extreme temperature conditions. So when I made it to Death Valley National Park that day, when I got to the park headquarters, which was not at the hottest part of the day actually, it was already 126 degrees. That's crazy hot. It got up to like 128, 29 degrees that day Fahrenheit. And so they had parts of the park closed because of the heat. And it was an unusual heat wave, but it's not so unusual right now because we're in a mega drought out there. So as climate warms, it exaggerates in places that are already like deserts. And that's something to consider linking back to groundwater and fluvial systems. That reduces the amount of snowpack and snowmelt on the mountain ranges out there, like in the Sierras and the Rockies, which means there's less runoff that can get into rivers and certainly less potential groundwater recharge. So holistically, this all fits together to realize that we have a problem when it comes to climate change on the planet. That goes to the reduced snowmelt, and in the desert, the snowmelt's the key, getting the snow packs. And in addition, since we're in this drought and climate is changing, it's getting warmer, there's not just less snow, but it's melting earlier in the year. So there's stretches of drought where there's less water, like during growing months of the year, where that poses problems for agricultural needs as well. So droughts restrict the water quantity in the desert, and this is a look at how serious the drought condition is in the west and southwest of the United States. Even the Pacific Northwest is having serious drought issues. This is a problem. And so if you're planning on moving out there, opening a business, whatever it might be, you need to consider what this looks like. And it's just a part of living in the desert. Unfortunately, it's changing how people can live in the desert. It's also going to drive the price of water very high over time. Wildfires are another consideration in the desert. So you kind of put all this with climate change in there, and then the drying of the soil. You don't have a really good fertile soil anyway. You get potential for more wildfires out west and southwest. That's certainly been the case over the last about decade. We've seen an increase in the severity, the size, and the scope of wildfires. So this is a wildfire in Saguaro National Park in Arizona near Tucson, and that's devastating because this is protected habitat. While wildfires are nature's natural way of kind of cleansing the land, there's a lot more of them than normally would have been. If you compare to 25, 30 years ago, the frequency, the size of these wildfires, it's much different. Wildfires also contribute to poor air quality conditions. They destroy habitat, which becomes problems for the ecosystem, all the animals and the plants that live there. I wanted to talk about something you may not know, which is cryptobiotic soil. Like, what the heck is that? Cryptobiotic soil is protected soil in the desert. So you may see areas that kind of get roped off in a national park. Deserts have soil that's made up of cyanobacteria, green algae, lichens, things of that nature, mosses, and they take decades to make. So they make this kind of crust on top of the soil, if there's any in the desert, and they're actually producing a healthy soil. So we don't want to step on them. We don't want to drive on them. We want to protect them because they create nutrients and provide a place for grasses and shrubs to grow, which also facilitate habitat for animals. So if you see something that looks like this, please don't step on it. It's cryptobiotic soil. Deserts need to be preserved. And here we're talking about all the hardships of deserts. Like I said, I want to retire out this way. Deserts are awesome. They are beautiful. And the geology out west and southwest in the United States is it's really spectacular. And they offer lots of opportunities for recreation, for enjoyment of nature. But if you're going to go out this way, you need to hike on the trails. You need to drive on designated paths and not get off the hidden path because you'll contribute to weathering and erosion, which can start a cascade of problems for mass wasting and loss of habitat. That goes to the habitat issue because desert biomes are home to numerous protected species of plants and animals. All kinds of birds and cacti. I might even say the endangered California condor hangs out in this area. Climate change affects their habitat. Wildfires affects their habitat. As temperatures warm, these animals may not be able to survive if there's not enough water or there's not enough things like cacti, saguaro cacti for them to live in. So think about how that relates to a whole ecosystem dependent on what happens in this environment, much like the ecosystem we talked about in glaciers for Arctic. I'd also say that make sure you preserve the land in the desert. There are so many vertebrate fossils of dinosaurs in the desert, and I am going to encourage you to not pick them up on public lands. I'm going to tell you it's a crime, and you know that by now. You've taken this course by PURPA, the Paleontological Resource Preservation Act. You got to have a permit to do this. So these are digs in Utah that were permitted under the supervision of a university that had a permit for the Bureau of Land Management, and our college participated in these. So legally, but don't go out and take fossils that belong to the federal government. You gotta have a permit. Be careful in areas that are protected. This is the Colorado National Monument, and this is a sign that shows what the fine is. I suspect these fines are going to go up. This is part of the creepy things that Casey Knockett did, and she was one of many people who've written all over these rocks. So archaeological sites like this one has a lot of petroglyphs, so people feel empowered to write over them, to destroy them, or add to them. Don't do that. If you see something like an arrowhead or a pottery shard or a point, a spear, whatever it might be that could be archaeological in some public lands, ARPA protects that. So make sure you do not move it even on public lands. That's the California condor on the left. This is actually Navajo Bridge, and this is the Colorado River. And as I have mentioned in fluvial, the Colorado used to be very, very mighty before we dammed it up at Hoover and Glen Canyon dams in two different places on the Colorado. But the California condor lives there. This is Condor 1. They are numbered and all monitored within that area. And occasionally you will find the condors hanging out at Navajo Bridge, which is off of Highway 89 going towards the North Rim, actually of the Grand Canyon. On the right, you see Glen Canyon Dam, and on the left, you see Lake Powell. And conservation of this water matters because we talked a lot about the bathtub ring. And Lake Powell's having the exact same issues as Lake Mead near Las Vegas, and conservation is a part of that process to keep this area thriving and surviving. Conservation projects exist through many national parks to try to help preserve the beauty, preserve water, preserve the land for the enjoyment of people, and protection of habitat for the desert biome. An example of that would be the Zion National Park shuttle system. This is used in the west side of the park where people want to go up and down the various hiking locations, and this is to reduce fossil fuel emissions, carbon emissions. It's to reduce noise and to reduce habitat destruction. So this is something that I would encourage you to do your homework on before you go to a national park, because these systems are becoming very crowded. Zion is now one of the most highly visited parks in the system. And it's not a surprise because it's absolutely an incredible place. But these shuttle systems are becoming more and more common at the very highly visited parks. So let's apply what you know. This is the Grand Canyon. And you see limestone at the top. That's the Kaibab limestone. And you see various different layers. You have been in this course long enough to start to piece together that every layer has a story. And I'm hoping that you will recognize that the story is different for each and every layer, and look at the geologic clues that are there. When it comes to the desert, you can do your part to conserve. You can do your part to pick up your trash when you're out there, to stay on the trail. You can do the things that matter. I want to encourage you to kind of piece together everything you've learned this semester and start to prepare for your final exam, going back and looking at all the features and all the rock types. That all matters for the end picture. My goal as you leave this course is that your perception and lens of how you view the natural world around you will be better informed and more complete, that you will see a story every time you see these landscapes. Maybe remember some of the names like hoodoos, various different names that you've learned, or volcanoes, or thermal features like geysers, and start to recognize the basic rock types and be looking for them when you're out in nature. Thank you so much for your time this semester, and I've had a great enjoyment of sharing it with you. As I leave you for the semester, I want to offer you one last moment of one of the most beautiful geologic sites that you've learned about this year, which is Glacier National Park. Thank you for all of your hard work. Hope you have learned a lot and continue your journey in geology.